This little visualizer that you see here, this is also something that I teach how you can create that from scratch. Data testing, I can drag and drop it here, and I could leverage and use a script, export the result, and you will have everything happening. Or sphere. Okay, so if I look now on what I output in the console, prediction of the sphere took 62 milliseconds and final classification sphere with 100% confidence, like shape generator, and I exported that to be able to predict, and we had also some rotation and this kind of things. Welcome to this tutorial on 3D point cloud classification. Today we are going to target principal component analysis, PCA, with random forest for close to real-time shape recognition. So this is really perfect if deep learning is overkill and if your hardware is limited. Without further ado, let's dive right in. Beautiful. So first, let me talk about the gains that we have to do that. Well, at the end of this tutorial, you will be able to extract meaningful features from raw point clouds. You will be able to implement a complete classification pipeline, and will be able to deploy for near real-time application and also achieve professional results with minimal computational resources. The second thing is that we are going to target a low computational footprint. We will want to have interpretable results, and we are specifically looking for something that is robust to noise, outlier, and scale to multiple object classes, right? So essentially, my setup is very simple. As always, I try to keep things as simple as possible to replicate and to extend. So we are going to leverage Python and the virtual environment management Anaconda. And with your terminal, what you can do is just create a new environment and activate it and install 4 main things. So NumPy, scikit-learn library, Open3D, and the last element, which is readPLY, because we want to be able to read PLY with labels. And I give you the function just below, so you can just download that. It will be easier for you. And for the rest, NumPy, you already know that. Scikit-learn is very good for machine learning at large, and Open3D, we'll just use it for visualization. Okay, so this is very minimal. Now, what about our workflow? Well, I designed it to work in 13 steps, so a bit longer than usual because there are a lot to unpack here, and know that this is only maybe one of the first stages. Right, so to extend from what we are going to cover, I link all the references, all the article, everything at the end of the video. So watch until there if you want to see also some specific really nice nuggets that are prepared for you. Without further ado, let's dive right onto the first stage, which is environment and setup. All right, so I'm all cozy in my IDE, and I import the library that I talked about just before. So NumPy, this is coming time with Python. This is just to have an idea about how long it takes for each step. This is scikit-learn. I just go and load only a specific set of methods from the full package and functions. And then this is Open3D, and this is the function, the module readPLY that I import as RD. And the readPLY, essentially, what I have here is the ability to read a PLY file with label and also to visualize a file with labels. So you have that for you to download. Feel free to take it and play around with it if this is useful to you. So first thing is I make sure this is my working directory. So I'm all set. I just need to execute this first stage and we are good to go. Beautiful. Now we can move on to the second stage, creating our 3D visualizer function. Beautiful. Now let me detail my little helper, visualize point cloud. So as you can see, I will take in an XYZ point cloud. And what I do is very simple, is I will essentially create an Open3D point cloud object, then fill the point with XYZ. I will also estimate the normals to have something a bit nicer to watch. And then I visualize it and I pass the list that hold only the point cloud. So just to test it, I created some random stuff, 1000 points, 3 columns, and I visualize it. So I press Shift Enter, and as you can see, you have the cube more or less that you can visualize. So this is very useful, and that's it for the helper function. Okay, let's move on to the third stage, creating a statistical outlier removal function. Great, so here this is an extra step. You don't need that, but this is for the more advanced version where you actually want to put that in production. This is one element that is shown in the 3D Segmentor OS course with the multiple training, with the PCA Inference. There's a thing that you get with the additional course. What I can show you is, for example, with this shape generator function that I will showcase in another video, you can drag and drop the point cloud and you will be able to generate such point cloud with labels for you to train from scratch without even having to gather data. So that can be very useful for you. And this little visualizer that you see here, this is also something that I teach how you can create that from scratch. You just use a bit of Python, JavaScript, and HTML and CSS. So that's all that is here. You can also get the code and get new stuff. I'm working on an X-Wing mode to fly around with that. And you can also generate shapes. You can see where I can generate shape, show the bounding box of my object, export that. And yeah, essentially you have a lot to do with this little nice stuff. I'm working on it also as we move around, but let me stop digressing and maybe get back to our matter at hand, which is going on to the next stage. All right, so here we want to remove our outliers. So what I do is I will keep in this function my point. I will search for the k nearest neighbors, and I have some kind of filtering function. So what you can see is I find the nearest neighbors. I get the indices and the distance. I compute the mean and the standard deviation of the distance, and I will use that to identify outliers. So whenever the point has a mean distance above this threshold, then it's dropped and I return only with a mask, right, my points. So I can show you what happens. So if I were to launch that, this is exactly what I was showcasing before. This is our little point cloud, right? Very nice. And you see that something is generated. Okay, so as you can see here, I will increase the point size. You have some gray floater point that I generate on purpose. And if I kill that, and we will visualize now the one that is cleaned, you see that you don't have all those outliers. So that can be cool stuff if you know that for sure you are dealing with outliers. This is not mandatory, but I wanted to give you the opportunity to do just that. Beautiful. Now, stage 4 is point cloud normalization. Right, so in here, what we want to do is normalize our point cloud, because you have to understand that we will have to pass that to some kind of classifier. At this stage, we don't know really what it will be, except if you read the title or the description. But if you want to switch it, which I don't lock you into using only one type of 3D machine learning application, you may need to normalize your data so that your classifier can handle that efficiently. Let me give you an example. If you train on data that is XYZ, okay, so let me show you an example that may be better, right? So I will load that again. So imagine that is point cloud on which you will train. You will use only the X and Y coordinate as features, and they all fall within that, okay? But then when you do the inference, for some reason the X and Y is there. If you did not, before training and all, like slide and translated that to the common frame of reference, you would have a problem, and maybe your model could not pick up any relationships or data points on which it can do some inference work, okay? So that's what I wanted to highlight. And here what I do is very simple. I just center and scale the point cloud to fit what we call a unit sphere. So I will make sure that our bounding box fit this unit sphere, and I will return my normalized point, the centroid, and the max distance. So whenever I execute that, this is what it looks like at the end. You have actually no difference visually, except that the scale is not at all the same. And if you investigate here the original bound, you had something varying between 0 and 12, 14, 2. And here we have something between 0 and 0, but it's units here. So between 0 and 1, if you take the absolute difference of that, okay? So this is all that we do. Again, this is not mandatory, but I wanted to give you how you can process with that. So now, okay, let's go on to stage 5, PCA Feature Extraction. Okay, so now let's move on to the heavy stuff, the principal component analysis, feature extraction. I already did a video on that, and I have a lot of detail in my book, 3D Data Science with Python, which I highly encourage you to read, either physically, like me, I love to have my books, or digitally on the O'Reilly platform. Took me a lot of time to write it. I pulled down everything to make it very clear, so hopefully that will be the best way to move forward with this book. But independently from that, and talking about right now, you see that I'm using a simplified version of PCA that is already implemented, and this is from scikit-learn. I have also other videos, and in the Segmentor OS, again, use something from scratch that you understand what's happening. But so that you're not lost, I took the liberty to took this auto draw so that you maybe understand a bit. So this is my 2-axis. I will make it in 2D, it will be simpler for us. And these are my point, right? So this is a kind of a distribution. You see that it's mostly linear, and the principal component analysis will really study the distribution to try to align something that can describe this point distribution with the minimal or the principal components. And as you can see here, if I were to find out what will minimize the variance in this distribution, you see that if I take something like this, I have a maximal variance, right, on this, but each point has a minimal variance to the line that I have. So this is super interesting. And the other properties that if you take the orthogonal stuff, this will be your second eigen vector. And this will be the first one. And here you have the eigenvalue of each point. So essentially, this is that you can do, and you can then leverage that, for example, to switch the frame of reference. Instead of being like this, you could orient it like this to find an oriented bounding box like this. So it's very handy. But here we'll use the eigenvalue as features to better describe our distribution, because being in this space, each variance element or each component, each eigenvalue, each feature that will delineate from that will have a lot of information to unpack, and that's what we want to do. Hopefully that is clear enough. Independently, you can see what I do here. So I do the PCA using the function, and I want 3 components. Because I have X, Y, Z, I just want 3 at this stage. So I don't use PCA for dimensionality reduction. I fit it to my points, and I get my eigenvalues, eigenvectors, and from there, I derived some features, the normalized eigenvalue, and specific set of features that could be useful to detect 3D shapes. As we mentioned, we want to be able to delineate between various shapes. And here, we'll use linearity, planarity, sphericity, as part of dimensionality feature, anisotropy, eigenentropy, and some more information. So anisotropy is really to see if you have a common variance among your point distribution, and this is the opposite is if you have chaos, basically a lot of noise, a lot of points everywhere, and the rest talks for itself. If you want to have more information, I remember that I wrote an article, so it's 3D voxel vs deep learning, I think it was in 2019. The point cloud carrier. So if I do books, cited by 200 close to. So, and here you have something. I need to investigate that in the figure. I think I show you various way to use that. It's not in here. Okay, so I think it's a bit below in a table that I may have put that. Yeah, so this is the explanation of the features. the eigenbase features. That's all that I'm using in this case, but these are derived and you can extract more information from there. That would be a good point to have. Okay, and at the end, all that I do is I will return my feature vector that will be composed of this various element. At this stage, I don't use the eigenvector in my feature vector. This is on purpose. This is something that we do in the course because it gets a lot of information in specific cases. But here, the trick is that you see that I perform the PCA not at a point level, but at a point cloud level. So this is a global signature. If you are in the Deep Learning OS course, this is exactly what we do with PointNet, where you have a global signature and a local signature. So this is what we are doing. Aside from PointNet that has this global signature versus local signature, we can also do that with PCA. This is what I do in here. But for now, let's focus on to something simple. We have a point cloud. We want to qualify that with a global shape signature. So I execute this, and you can see here what I have. So this is based on our normalized point cloud, right? So the scene. So this may not mean a lot at this stage. This is why we'll do something later on, but essentially you see that it works. And we have a linearity, planarity, sphericity, anisotropy, and eigenentropy. Beautiful. Now it's time to get onto great stuff. Stage 6, testing on various geometric shapes. For our various geometric shapes, I create 4 of them: box, cylinder, plane, and sphere. And let me show you. This is PCA classification, data simple. That's what we have: the box, the cylinder, the plane, and the sphere. And again, you can find that just down below. I give you access to these datasets. So in here, what I do is I just loop around and I will read. I drop the labels. They have no labels. I normalize the cloud. I visualize to make sure this is what I have. And I execute my PCA feature computation. So if I do that, you see, this is first the cube. Beautiful. Then we have the cylinder. Then we have a plane. And then we have a sphere. Great. Now I print a lot of stuff. So if we look at the console, first off on the box, we see that we have something close to 0.33. We have a small linearity, small planarity, high sphericity, high eigenentropy, and we have a normal vector that makes no sense. This is normal because it's something composed of a lot of various planar shapes, and this is a bit hard to decipher. Now for the cylinder, this may be a bit more pragmatic. We have a better delineation, eigenentropy is high, and the sphericity is middle, very low planarity, linearity is okay, and for the plane we should have a very high anisotropy, so it's very, very structured, very low sphericity, of course, and we have a high planarity, so it makes sense. And for the sphere, we should have a high sphericity, low planarity, low eigenentropy, and low anisotropy. So that makes perfect sense, and you see how these features could be very useful, because then you can use that to basically know more or less if this shape is more spherical or the shape is more planar. So the next stage is what you've been waiting for. Well, now it's time to attack random forest classifier definition. All right, so it's time to train a 3D machine learning model on our feature set. And I'm very clear here. I don't intend to give you the way already to have the most powerful machine learning system. I will talk about how to improve very, very efficiently just at the end, but bear with me. Here, I just want to show you how it works and what you need to take care of when you design your training routine. So as you can see, this is a very simple function that will take in my features. I don't even take the coordinates, the labels, and the number of estimators. So this is called a hyperparameter because it's a parameter that is specific to the training process of my random forest machine learning model. And the max depth, for now, I don't set that up. This is also a hyperparameter. And all the rest I do that inside. So the first thing is that we split our data into two parts, training and validation sets. By convention, we use train and test, but really to clarify, normally you have a train and validation set on which you want to check if the result you had using the training data actually propagate to the validation step. And then you hold out a test set that is nowhere close to the training modality of your pipeline so that you can evaluate close to real world predictions. Okay, so in here, something simple is that I leave out 25% of my full data. This is randomly taken, and I leave that out of my training set, and this is what will constitute my testing set. So X is really the data, the features, and Y is the labels. This is the convention. Now I will initialize and train the classifier, and in here I create a variable classifier, and I will use the random forest classifier directly. And you can see that I use the parameter that I gave above. For the max depth, I use also this parameter if we need to set it up. And this is a simple number. I explain why 42. It's a funny joke from a book, but essentially this is just to replicate the experiment with this random state. And we will use all available cores. So this is why I do that. After that, my classifier is defined, and all we do is we train, and for that we use the fit. So we fit our classifier to the training data, and we keep in the training label, of course, to match that together, to be able to backpropagate and adjust the various elements in our random forest. Okay, and then after that we evaluate, and for that this is just using the predict on the X test, and we compute the accuracy in here. Also, because it's a random forest, what is super cool is that you can actually compute the feature importance that played a major role into the definition of the result that you get. So this is all that we do, and nothing happened because I don't call it afterward, but that is all for defining our training random forest function. That was not so hard, was it? Okay, let's move on to generating a simulated training dataset. All right, this is awesome. Now let me simulate training data, so features, okay, to test out and train our machine learning model with this simulated data. So this is also something where I want to emphasize. This is the kind of things that I like to do whenever I design solution for any challenge that you may have. And if you want to be innovative, so it's working step by step. And here, the first easier step is to work with very like simple synthetic data before going on to real world data. Okay, so the synthetic data that I simulate is very simple. We will create three shape classes: a sphere, a cylinder, and a plane. And this is what I do. This is my sphere, this is my cylinder, and this is my plane. And then we will combine the various features and we will create labels from there. So this is all that I'm doing. I execute. And if I take my sphere as feature, you will see that this is how it looks like. It's just an array that is made of my various sphere feature. Now, stage 9 is to actually train the classifier using this simulated training dataset. We are now ready for training the classifier, and you will see that it's actually quite quick. But again, this is a synthetic data, so this is supposed to be quick. This is what I do. I will hold out classifier importance and data split from the execution of my trained random forest. I pass in all my filter, all my label, and then I want at the end to print out the feature name and the feature importance that we have. So when I do that, that's already done. So it's maybe less than a second to train on what I have. And okay, the report is very good because we don't have so many data. As you can see, our support is around 125 per class, which is a good starting point, but this is something where we have a balanced data set. This is usually not the case with real world data. That's good to have a test to see if everything works properly. Now you see the feature importance. We see that we have a high feature importance for the eigenvalue, and a lower feature importance for the eigenentropy, or higher, sorry, feature importance for the eigenentropy, the sphericity, the planarity, the linearity, and the lower for the eigenvalue. So this is very good because it hints at what we had in our head before. We have data to support our first hypothesis that we could leverage this kind of information to actually detect and classify shapes. Now we move on to stage 10, which is defining the inference function pipeline. We are not yet there. We need to actually use the train model and do inference on unseen data, right? Or data that we left out to test on it. And one type of data that we left out was the one that I generated, that is actually existing, and we'll see already on that what happens, but later on. Now let's define the inference function. So as you can see, this is really a state of mind where you design kind of a pipeline where you take in the points, the classifier, and if you want to do pre-processing or not. And the variables is really if you want to output information or not. So what I have here is I actually will time to get the processing time of each individual step. So I use the pre-processing, statistical outlier filter, I use the normalization, the feature extraction, and then I do the classification. And the classification, I just don't fit, I just do the predict on the feature set. And I will retain only the first element from my prediction that I can use later on. So this is what I have, and this is what I will execute. But before that, just understand that if you want to use, and that's the goal at the end, to use that outside of this script as a standalone, you will need to make sure that he has access to the pre-processing step, normalization, so all the steps that you used for creating the training data. You need to be in the exact same setup or as close as possible as the training data. Because if you don't do that, you risk you actually risk being stuck with generalization capabilities. So whenever you will get out of scope, it will be very bad results because you cannot generalize, because you didn't see something, because you didn't took the same exact funnel. We're almost there. Stage 11 is to test the inference on dummy data. All right, so for testing the inference on simulated data, this is what I do. I create a random point cloud representing a plane, flat, okay, in the Z dimension. So this is really simple. I will show you what my plane look like, and then I will classify directly. So for that, I will just execute my classify point cloud and hold that in result, and I will print some stuff. So if I do that, first we look that it's a plane which is a bit noisy. It's like almost like a little flat cube, right? And I will close that. And once I close that, it stops the render blocking function of Open3D and it launches my classification pipeline. And what you see is that the classification of the plane was achieved in less than a second. And we can push that much higher. So this is what I call close to real time. Real time, you are in millisecond kind of frame of reference. Here you are still below 1 second, so you are in the millisecond realm. So it will be 720 milliseconds. So this is still very good. And you see what takes time. It's not the normalization, it's not the feature extraction. The classification take around 53 milliseconds. So what really all in all take time is, no, the total process time is 59 milliseconds. I'm sorry, so it is very close to real time. No, this was not 700. That's the confidence on which you can predict that is a plane. So this is my plane, and this is the confidence score. So you see that with this kind of methods, you can actually, with a bit of tips and tricks, like engineering, we are using Python. This is a language where you don't need to compile. This is done for you, and you already get something that you can leverage almost close to real-time scenarios. So this is something that will not really noticed, right? The frame rate of your your screen is usually not for gamers, but that would be 10 to 20 milliseconds. So you see, we are pretty close to that. Beautiful. And the second thing is it predicted correctly that that is a plane. So now let's find out on real data. Okay, let's extend in stage 12 to running the inference on actual generated shapes. When I say real data, I mean generated data still, but really not made out in Python. These are things that I modeled outside of Python, and for that I used my little like shape generator, and I exported that to be able to predict. And we had also some rotation and this kind of things. Anyway, let me get back to my code. So you see that we have the 4 shape, and I will read that. I just took the function that I did above, and essentially we don't need to do the feature extraction because this is part of the classifier point cloud. So let me delete that. I think that was a reminder from what I did before when I copy pasted it, and I will execute that. So this is my cube. Okay, after we have our cylinder, we have our plane, and we have our sphere. Okay, so if I look now on what I output in the console, prediction of the sphere took 62 milliseconds, and final classification sphere with 100% confidence. How amazing is that? Now, for the plane, final classification plane with 75% confidence. For the cylinder, final classification cylinder with 97% confidence. This is amazing. And the box, final classification sphere with 100% confidence. This is a trick part that I wanted to show you. We didn't train on the box, and he has not the ability to know a label that it was not passed to. This is really an ability that you will find in something that can generalize, so more AGI stuff that is coming out more and more. I will talk more on that later, but you can see what you can expect to get from this kind of element. Beautiful. And finally, let me talk about how you can go further with super nice ideas. We're already there, and I'm very happy because I wanted to make sure that I don't hit the 30-minute mark before you being able to have all the various stages that we approach here. This is actually not easy to grasp. I hope I made it very simple for you to understand the concepts. So how can you extend from that? This is a basic setup, right? But you have everything to extend from there. The first thing will be, how can you train on multiple real-world data set at scale? So that's the first thing. And this is what I give, this script, this is what I give in the Segmentor OS course that allows you to actually take a folder. This is what it looks like. You have a folder filled with a lot of data. So here it's only one in training, and 3, but you can have a lot more. And yeah, actually, let me show you. Another shape generator is somewhere else. But yeah, you have a lot of data training. You use that to define a model, you export that, and you will use that then thereafter. Okay, so that's the first thing. If you want to take the shortcut again, the 3D Segmentor OS is there for you. But if you want to go into hardcore mode, you can do that on your own, of course. Then the second stuff is, how can you prepare the inference? So here we did the inference within the script. What is good is that you create a single element and you pass that to some kind of GUI that allows you to do that for you. And yeah, I can show you maybe what that would look like. I think I have a GUI somewhere that we created for the course interface script. Yeah, so what I will do is go there, I will put the change directory, I will go that, and I will call app.py. And normally, no, yeah, I need to call Python app.py. Sorry about that. Okay, and that opened a development environment, and this means that I could now load a point cloud from the classification data testing, I can drag and drop it here, and I could leverage and use a script, export the result, and you will have everything happening. So it will just put the inference key there, and that will do the inference for you. And if you want to combine that with the viewer, at the end, it pushes that to your viewer elements, and you're able to look at the various predictions. This is fantastic. So that will be one way you can extend. There's a creation that we do, but yeah, this is, I love it always to show you where you can go if you push more and more. So this is actually what I meant the creation of the hub. And the fourth, scientifically more grounded element that is super interesting to check out is how you can improve the classifier. And for that, I talk about three things. So first thing is talking about the features. You have ways to use better features. Here, we export the feature importance, but we don't really do anything with that information. So maybe we could engineer the amount of feature that we need. And maybe we can put out more feature. Why not use XYZ? Why not use something else? This is a first layer. If you are stuck at a little ceiling with the metrics, you can push out there. Then, if something is very close to the production-ready metrics, just tune your hyperparameters. Here we used 100 trees, but you can have much wider forest or use other elements within. And the last stage is, what about changing the model? So, of course, here I did not talk so much about the model at hand, random forest. It's well studied, but it's very powerful classical model, and this helps you go without going with deep learning necessarily. But at any point, whenever you have enough data, you can go and check out deep learning models, like the one we show in the 3D deep learning course, PointNet, KPConv, SuperPoint Transformer. So any of the model that is able to handle point element. And that's also another thing. We reason at the point cloud level. And this is in here, we reason at the point level. So that gives you also an idea about local context, and you can get prediction and go into semantic segmentation scenarios, right? Where each individual unit, which is a point, will have a class prediction. Whereas here it's each point cloud is our entity gets a prediction, right? I think we are good with all of that. Hope you had a lot of fun. I certainly did, and I will continue to push out new, useful, hands-on knowledge for you so that you can learn and grow at your own pace. Beautiful, we went through, there's 13 stages. If you want to extend, I cannot encourage you more than go have a deep look in the 3D Segmentor OS course. That's all that and much more. Also the code with a license to use commercially. And if you want to be one of the lucky one to get your hands onto my new book, 3D Data Science with Python, you will find a lot there. It's published with O'Reilly and it's coming in April. See you in the next video. Bye-bye.